Hey everybody, in this video we are going to go over a 20 question multiple choice test that I created based on the topic of electrons. So without further ado, let's get started. So before I start, let me put a decimal place there because I forgot to. And now let's read the question. Calculate the energy emitted by a mole of photons with a wavelength of 600 nanometers, which corresponds to orange light, which is a type of visible light that we see. Now, this question requires us to calculate the energy emitted by a mole of photons, and we're given the wavelength, which is 600 nanometers. Now, if we want to use the equation C equals lambda V, we have to make sure the wavelength is in meters and not nanometers. So let's get to that. 600 nanometers times 10 to the 9 meters. Let me just redo that. 10 to the negative 9 meters per nanometer. And the nanometers cancel out, and we're left with 600. And let me add the decimal place since I forgot to do that. So decimal place there. 600 times 10 to the negative 9 meters is our wavelength. Now we have to plug this into the equation. So this times v is equal to the speed of light, which is 3.00 times 10 to the 8 meters per second. Now using a calculator, so let me just pull out a calculator. 3 times 10 to the 8 divided by 600 times 10 to the negative 9, and we get that our frequency is going to be 5.00 times 10 to the 14 hertz. Now, that's not what hertz is, it's an H. Alright, HC. Now, we have to find the energy for one photon. So, energy for one photon is equal to Planck's constant, 6.626 times 10 to the negative 34. And this is multiplied by the frequency, which is 5.00 times 10 to the 14 hertz. Doing the math, let's see. I'm going to type this into my calculator, so give me a moment. And I get that the energy for one photon is going to be 3.31 times 10 to the negative 19 joules. Now, let's take a step forward and let's think about what the question is asking. This is for one photon. They want a mole of photons. So naturally, if this is for one photon, then you have to multiply this by the number of photons in a mole in order to get the energy for a mole of photons. So let me just clear this page and let me write this. 3.31 times 10 to the negative 19 joules per photon, and I'm going to abbreviate it, and we have to calculate for a mole of photons. So in a mole of photons there are 6.022 times 10 to the 23rd photons per mole of photons. And doing the math, let's see, times 6.022 times 10 to the 23rd, we get that in a mole of photons there is approximately 199,509 joules of energy. So we have to make it in kilojoules since, the answer is in kilojoules. So let's multiply this even further. And there are, 10 to the third joules in a kilojoule. And in the end, we end up getting 2.00 times 10 to the second kilojoules. And note that there are 3 sig figs because over here there are 3 sig figs, and when you multiply it, this answer should have 3 sig figs, and then your final answer should also have 3 sig figs. And I almost forgot, but let's put per mole of photons at the bottom, since that was never canceled out, only the joules were canceled out. So this would be our answer. And 2.00 times 10 to the second, it's the same thing as 200 kilojoules per mole of photons, and that would be C. So now let's move on to the next question. Scientists use emission spectrums to analyze stars and determine their elemental compositions, since every element has a unique emission spectrum. What is an emission spectrum? So this is a definition. It's not the wavelength that atoms or compounds absorb. Instead, it's the wavelength that atoms or compounds reflect or emit. I mean, they essentially mean the same thing, or they mean really close to the same thing. And C, the type of pollution emitted by each atom. That doesn't make any sense. And D, the types of heat emitted by each atom or compound. Now remember, this is electromagnetic energy we're looking at. Heat is another form of energy, and we're not looking at that. So the answer is B, and let's move forward. 3. The energy for a mole of electrons, depending on the principal energy level, is negative 1313 kilojoules per n squared. And this describes the energy of a mole of electrons, as I said, for a hydrogen atom. Find the energy associated when one electron jumps from n equals 2 to n equals 1 in a hydrogen atom. So let's draw the diagram first. So n equals 2 to, n equals 1. If the electron hops from n equals 2 to n equals 1, it's going to be losing energy. And if something loses energy, that means that the change in energy is going to be negative. So let's cross out two answers right off the bat. B and D are out of the game. Now we have A or C. Now let's just do the math and figure out what the change in energy is for a mole of electrons, since this equation gives us the energy for a mole of electrons. So on the next page, we know that the change in energy for a mole of electrons, and that's what N means, it's just a mole, is equal to the final energy phase minus the initial energy phase. The final energy phase is, n equals 1, so it would be negative 1313 over 1 squared minus, now what's the initial energy state? Well, it was from here to here, so this is the initial. So it would be negative 1313 over 2 squared. And if you type that to a calculator, negative 1313 divided by 1 squared, which is just 1. And you just subtract it by negative 1313 divided by 4, since 2 squared is 4. And you get that the change in energy is negative 984.8 kilojoules. And this is the change in energy for a mole of electrons. So let me write that. This is for 1 mole of electrons, just to be clear. Now we need it for 1 electron. So how do we do it for 1 electron? Well, we simply take moles of electrons and we change it to just 1 electron. So negative 984.8 kilojoules per mole of electrons times, well, there's 6.022 times 10 to the 23rd. Oh, I'm doing it wrong. I'm supposed to put that on the bottom. So this is supposed to be 6.022 times 10 to the 23rd electrons per mole of electrons. And these two cancel out. And we're left with, well, let's see, divide by 6.022 times 10 to the 23rd. Make sure you have parentheses, and we get that for 1 electron, we have a change in energy of 1.64. Well, let's do 4 sig fig, since that was what we had. 1.635 times 10 to the negative 21 kilojoules. And that is our answer. Now, you might be wondering, why did we do 4 sig figs and not 1? Well, these numbers, 1 and 2 squared, are exact numbers, meaning that if you're n equals 1, you're exactly 1, so it has an infinite number of sig figs, so therefore we can essentially ignore the sig figs on these two numbers. So, which answer matches this? Well, let's see. Negative 1.635 times 10 to the negative 21 kilojoules, and that looks like C. So let's move forward to number 4. So for number 4, an electron staircase would be very helpful, and remember, you're supposed to memorize how to draw it, so I just put it here because, I didn't want to write it out because it would take forever. So rank the orbitals in terms of energy. So in terms of energy, remember, the staircase tells us the order in which they go in terms of energy. So let's look at this. So we have to compare 4s, 4p, 4f, and 3d. So let's start, I think the lowest energy would be 4s because it starts here. And then second goes 3d, and then 4p, and then where's 4f? Oh, 4f is all the way here. So I just found the order. So it would be 4s comes first, and then 3d comes next, and then 4p comes after, and then finally you have 4f. And that's our answer. So which one's the right answer? So it looks like C is our answer for number 4. Number 5, for a certain principal energy level n, where n is greater than 3, how many f orbitals are there? So for a certain principal energy level n, where n is greater than 3, so let's just say n is 4 because 4 is greater than 3, how many f orbitals are there? So for a number like 4, how many 4f orbitals are there? So if you remember, there are 7 f orbitals in the 4f sublevel, so the answer is 7. And you might be tempted to write 14 because there are 14 electrons in the f orbitals altogether, but each orbital holds 2, so there are 7 orbitals total that can hold a total of 14 electrons, but the question's asking for orbitals, so the answer is D. Number 6. AU has this electron configuration. I wrote it out for you. And this electron configuration is an exception to which of the 4 rules? So Hund's rule states that electrons can be single first before they pair up. So something that would violate Hund's rule would be if something like this happens, where you have maybe 2 electrons that are alone, and then suddenly you're pairing up, and Hund's rule is like, wait a second, you can't pair up until all the orbitals in the sublevel are filled halfway. So for example, if this is 2p, Hund's rule states that these orbitals have to have at least 1 electron in there before they start pairing up. So in this case, this violates Hund's rule since the electrons decided to pair up before even filling all of it with at least 1 electron. So remember, Hund's rule means that you need at least 1 electron in each orbital before you can start pairing up, and this applies to just one sublevel, as you can see. So gold is not violating this rule since, you know, for 6s there's just 1 electron, and for the 4f's, you know, I could draw 7 lines if I want to, but all of these have been completely filled, so no violation there, and for 5d10 they're completely filled, so no violation there. So it's not violating Hund's rule. So what about off-ball principle? Well, for this idea, remember, off-ball principle states that the electrons have to fill in the lower energy levels before going up. So in this case, these are written in order in terms of energy. So in this case, the gold skipped 6s and it went straight to the D sublevel, if you might remember from the video. So because it decided to take 1 electron and move it up to a higher energy level, this violates off-ball principle since the electrons are not ordered from least to greatest, and the lower electrons are not filled first because the 6s1 is not completely filled and it decided to go straight to there. And, you know, that's a violation of off-Ball's principle. So that's the answer. C is wrong because the Pauli exclusion principle only applies when you're comparing 2 electrons, and D is wrong because Coulomb's law has nothing to do with electron configuration. Now, let's move on to the next question. Number 7. As an electron gets closer to the nucleus, the electrostatic force between the electron and the nucleus blank and the charge of the electron blank. So let's draw a diagram. As the electron gets closer and closer to the nucleus, the electrostatic force, or the attractive force between the electron and the nucleus, will increase because, according to Coulomb's law, as, you know, distance decreases, the attraction increases. So this is Coulomb's law, and as you can see, as an electron gets closer, R will decrease, but in consequence, F will increase because R is on the bottom and F is on the top. So therefore, in this case, increase is the first part, and C and D are wrong. Now, what about the second part? The charge of an electron, does it change as it gets closer to the nucleus? Well, I don't think so. So B is our answer, and let's move on. Number 8. Valence electrons, at least for the main group metals in groups 1, 2, 13 through 18, are typically located in which 2 orbitals? Now the answer is A, because if you remember, the octet rule states that the s and p orbitals have to be fully filled, which means 8 electrons, to be happy. So this is related to octet rule, and although D and F electrons can be valence electrons. These only occur when you're looking at transition metals, and that would be when the d electrons can be valence electrons, or if you're looking at actinides or lanthanides, and in that case the f orbitals could be valence electrons. And I wrote that in a note at the bottom of the video in the description for one of the videos, and go ahead and read that if you want to learn more about valence electrons. So in this case, A is our answer because for the main group metals at least, the s and p electrons are the main valence electrons that we're looking at because they are the ones that satisfy the octet rule. Now let's look at number 9. Write the abbreviated electron configuration for rubidium. So I pulled out a periodic table, and remember, you can use a periodic table on this test because, it's impossible to memorize where everything is on the periodic table. That would be kind of unfair. So in this case, rubidium's right there, and the previous noble gas is krypton, so we can assume that krypton will be like that. And then we have to move to the next one, and notice how rubidium just has one more electron than krypton, so we only need to add one more electron. And krypton is in the 4p level, so the next one after 4p, if you remember from the staircase, is 5s. And 5s, we only need one 5s electron, so 5s1. And this is the abbreviated electron configuration for rubidium, and that would be C. Now let's look at number 10. Find the 4 quantum numbers associated with the final electron of potassium 2+. Now what an odd thing to look at. Let's figure out what potassium 2+ looks like. We know that potassium is, well, looking at the periodic table, potassium's right there, and the previous noble gas is argon, so let's write argon. And then potassium just has one more electron than argon, so we have to add one more. And since this is 3p, then the next one is 4s, so we just have to add one 4s electron, and that's the electron configuration for potassium. So let me change this because we're losing 2 electrons. Let's actually expand argon's electron configuration, and that would be 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s1. So all of this belongs to argon, and we just expanded it. So we have to remove 2 electrons since it's K2+. So which ones do we remove? Well, we're going to remove the one with the highest N, so that's gone. But we need to remove one more electron. So what's the next highest N? Well, it's the 3s. Do we choose a S electron or P electron to remove? Well, we typically choose the one with the higher energy to remove. So in this case, since the N's are tied, then we look at the energy levels, and since 3p has more energy than 3s, we remove a 3p electron, and we end up with K2+. Will have an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p5. And it's asking for the quantum number for the final electron of potassium 2+. So let's look at where the final electron is. So let's draw the 3p sublevel. 3p has 3 lines, and it's 3p5, so it's 1, 2, 3, 4, 5. And the final electron that I drew was this guy. So let's draw the number line. Remember, this is going to be quantum numbers. And then let's do 4 numbers. So since this is 3p, then the first number is 3, the second number is p, and p correlates to 1. And then the next one is the number line, which is 0. And then last but not least, since the arrow is pointing down, then it's -1/2. And that corresponds to 310, -1/2 D. Next question. Provide a reasonable explanation for why helium does not have a measurable electronegativity value. Now, remember, electronegativity is how badly something wants to attract an electron pair. So for example, helium might want to attract an electron pair to itself. But in this case, it says, oh, helium doesn't have a measurable electronegativity. Why might that be? Let's read our explanations. Helium's electrons are located very close to the nucleus. That is true. But wouldn't that mean that it would have a very high electronegativity value since electrons are located closer, are more attracted? So that doesn't explain anything. Nope. Helium has a Zeph of 2. That would explain why it would have a low electronegativity since things with a low Zeph have a low electronegativity. But in this case, it doesn't make any sense here, so no. Because remember, the question says it does not have a measurable electronegativity value. And this is telling us that it might have a low electronegativity value. But just to be clear, this atom is so small that a Zeph of 2 can be very, very impactful, because a Zeph of 2 means that 2 protons are attracting, the electrons around it. And for electron to be that close, and even though it's a small charge, it can be pretty powerful, especially because the electrons are close. So don't be deceived by the Zeph of 2 just because it has a Zeph of 2. You have to also think about the atomic size. But since that doesn't apply to this question, let's look at the other answer choices. Helium does not want to attract any electron pairs since it has a full 1s orbital and is relatively stable and unreactive. Now this makes sense, since if helium doesn't like to attract electron pairs, then it won't have an electronegativity in the first place, since electronegativity is describing how badly something wants an electron, and if something doesn't want an electron, then you can't really measure that, so C makes perfect sense. D. Helium is too small to observe an electronegativity value for. So this is wrong, because we observe electronegativity values for hydrogen, and hydrogen is smaller than helium, so this makes 0 sense. Next question. So explain why metals generally have a lower ionization energy than nonmetals. Now remember, metals are these guys, and nonmetals are these guys. So metals have a low Zeph, while nonmetals have a high Zeph, so the electrons in metals are more attracted to the nucleus. Oh, wait a second. Why would the electrons be more attracted to the nucleus if they have a low Zeph? And let's read on. And are easier to remove than the electrons in nonmetals. So we have two contradictory things here. The electrons in metals are more attracted, yet they are easier to remove. I think this is contradictory. And it's also wrong because electrons in metals should be less attracted to the nucleus and should be easier to remove than electrons in nonmetals. So since a part of the answer is technically wrong, then the entire answer is wrong. Let's look at B. Nonmetals have a higher Zeph than metals. So I agree with that because nonmetals are toward the right. So their electrons are more strongly attracted to the nucleus, which causes nonmetals to have a higher ionization energy than metals. Well, that makes sense. Higher Zeph, higher ionization energy. And this answers our question because saying that nonmetals have a higher ionization energy than metals is the same thing as saying that metals have a lower ionization energy than nonmetals. So B is our answer, and we're not going to read C and D. You can read those by yourself. And keep in mind that C and D are wrong. So, next question. Sodium metal has a threshold frequency of 4.40 times 10 to the 14 hertz. Find the minimum amount of energy a photon needs to eject an electron off of sodium metal. So the threshold frequency is related to the photoelectric effect, and it states that a photon needs to have a minimum frequency in order to eject an electron off of it. So in this case, since sodium metal has a threshold frequency of this, it means that the photon needs a minimum frequency of this in order to eject an electron off of sodium metal. So we have to find the energy associated with that frequency, and that would be the minimum energy needed to eject an electron off. So I showed all the work that's required for this question. I converted the threshold frequency into the minimum amount of energy a photon needs, and it becomes this. But notice the answers are in 10 to the negative 16, and we have 10 to the negative 19. So we have to convert joules to another unit, and I found that by converting joules to millijoules, we get C, because 2.92 times 10 to the negative 19 joules times a millijoules per 10 to the negative 3 joules is equal to C, which is this. And notice how I just converted the units from joules to millijoules, and I ended up getting C. So this question was a bit tricky because of the different units for energy, but if you did trial and error, I'm sure it would have been fine. So let's move on to the next question. Barney the dinosaur has a dense quantity of xenon gas, so some xenon gas in a container. Barney hangs the container of xenon gas off a string attached through the roof. So let me draw Barney's purple hand. And then he puts a strong magnet made of neodymium near the container. So he has this super cool magnet that he's going to use. So this magnet is going to look like that. So what will happen? So we have to determine if xenon is paramagnetic or diamagnetic in order to see what happens when xenon, reacts to the magnet. So I wrote out the electron configuration for xenon using the abbreviated form. I took the previous noble gas and I, did the other orbitals. And notice how all these orbitals are completely filled. And when they're completely filled, it means that there are up and down arrows in every single orbital. And that's what it means to be completely filled. Since if you try drawing all of these orbital diagrams, you'll see that they will all have up and down arrows. And because there are no unpaired electrons, this xenon will be diamagnetic. And therefore, A and B are out. So if something is diamagnetic, does that mean a magnet repels it or attracts it? Well, if something is diamagnetic, the magnet will repel it. So therefore, if you put a magnet there, then the xenon will move away from the magnet. So, since there's xenon here and there's a magnet, the magnet will repel the xenon, and then the xenon will, force itself to be, move to the right if the magnet is introduced to the left, and therefore D is our answer. So this one was a little bit creative, I admit. So let's move on to the next question. How many completely filled p orbitals are present in the ground state chlorine atom? Now if we do chlorine, it's 1s2, 2s2, 2p6, 3s2, and 3p5. So let's look at the p orbitals. So the 2p orbitals are completely filled, so there are 3 2p orbitals, and they're completely filled in this case. And then for the 3p orbitals, we have 5 out of 6, so 1, 2, 3, 4, 5, and that's 5 out of 6 for 3p. Now how many completely filled p orbitals are there? Well, there's 1 completely filled, 2, 3, 4, 5. So there are 5 completely filled p orbitals in a ground state chlorine atom. This is half filled because it only has 1 out of 2 electrons. So D is our answer. Next question. Which set of quantum numbers cannot correspond to an electron in a ground state gas phase PD atom? Now I'm just going to show you the answer. It's B, because if you look at B, it's saying that the quantum number for one of the electrons is 3f, and that's from the first two. And notice how 3f doesn't exist, because it's not part of that staircase that you remembered, so therefore it doesn't exist. And in addition, L is supposed to be n minus 1 at most, and notice that 3 minus 1 is 2, so therefore L can be at most 2, but since L is 3, then, it's wrong. So 16 is B. Let's take a look at number 17. The electronegativity of gallium is greater than that of aluminum, which is the best explanation for this difference. So gallium is here and aluminum is here, and notice how gallium is below aluminum, and if something is below another thing, you expect it to have a lower electronegativity, since electronegativity decreases down the groups. So why is gallium higher in electronegativity than aluminum? Well, the best way to find out in this case is just to read the answer choices and see which one makes sense. Gallium is larger than aluminum, so its valence electrons experience less electron-electron repulsion. That's true, but does that explain why the electronegativity is greater? Well, not really, because electron-electron repulsion has to do with the atomic size, and since we're talking about electronegativity, this wouldn't be a very good explanation for the reason why gallium might have a higher electronegativity than aluminum. So let's read B. Gallium has more protons than aluminum, so its valence electrons are more attracted to the nucleus. Now, at first you might read this and say, aha, that sounds correct. But if you think about it, this is basically saying since one element has more protons than the other, it's more attracted, so it has a higher electronegativity. Now, if we find a counterexample to this logic, then it's wrong. So if we compare the electronegativities of iodine and fluorine, we could argue that, oh, well, iodine has a higher atomic number, or it has more protons than fluorine, so the electrons in iodine are more attracted to the nucleus. Now, that's logically flawed because we know that iodine has a lower electronegativity than fluorine, which is the most electronegative element on the periodic table, and therefore justifying that this has a higher electronegativity than this based on the size is incorrect, since if you do it for fluorine versus iodine, you'll see that the exact opposite is true. You'll see that the valence electrons in iodine are actually less attracted to the nucleus, and because of that, iodine would be a less electronegative element. So therefore, B is out of the game. And I mean, I'm talking about this in terms of valence electrons, but really electronegativity has to do with how badly it wants to attract covalent pairs. And a valence electron is part of a covalent pair, so that's why I'm talking about it in terms of valence electrons rather than a covalent bond, since the valence electron is technically part of the covalent bond, or the pair of electrons, as you'll see in future videos when we talk about covalent bonding. So let's take a look at C. Gallium has a filled 3D sublevel whose electrons incompletely screen the nucleus. Now this rings a bell. Incompletely screening the nucleus has to do with Zeph. And if we think about it, let's just draw gallium, and let's just draw, maybe 4 circles, since, it has 4 p electrons according to the periodic table, and aluminum has, well, just 3 p electrons, so let's just draw 3 rings. And if we think about it, the 3D sublevel is located on the 3rd ring, and if these electrons incompletely screen the nucleus, that means that the Zeph is higher than normal for gallium. So as you remember, Zeph for an atom is equal to its number of valence electrons, so the Zeph of aluminum and gallium is expected to be 3. But since the electrons in gallium, specifically the 3D electrons, are incompletely screening it, you have a Zeph that's higher than normal for gallium. So gallium might have a Zeph of 6 as opposed to 3, while aluminum has a Zeph of 3. So because gallium has a higher Zeph than normal because its 3D electrons incompletely shield the valence electrons, then gallium will experience a higher electronegativity since it has a higher Zeph, which means that the valence electrons outside are more attracted to the nucleus. So as a result, this actually makes perfect sense. Since gallium has a higher Zeph than normal, then gallium would have a higher electronegativity than aluminum. And you might be wondering, well, the electrons in gallium are farther away, so shouldn't they be less attracted? Well, although they're farther away, the Zeph for gallium is much higher than normal, and because of that, that Zeph overcomes, the increased distance from the nucleus, and therefore gallium has a slightly higher electronegativity than aluminum. So I'd say C is a perfect answer. Now let's look at D. Gallium experiences significant relativistic effects which contract the valence orbitals. Now, this doesn't make any sense for me personally because I don't know what this word means. And if I know for sure that one of the answer choices makes sense, I usually stay away from things I don't understand. So D is out of the picture, and indeed number 17 is C because I checked the answer and it says it's C, so it's C. Number 18. In which list are the elements in order of increasing first ionization energy? So notice how the 4 elements are calcium, silicon, phosphorus, and nitrogen. So let's circle those on our periodic table. Calcium, silicon, phosphorus, and nitrogen. So you have to order these in increasing first ionization energy. So which one would have the lowest first ionization energy? Well, the one at the lowest would be the one that has electrons that are the furthest and least attracted. Now, I think calcium gets the award for this because calcium has 4s2, and these valence electrons are located farther than these 3 p electrons, or the 2p electrons. So as a result, I think that calcium is going to have the lowest first ionization energy. Now, we have to compare the last three: silicon, phosphorus, and nitrogen. Now, I can tell you which one has the highest ionization energy. It would be nitrogen, because its electrons are located closest to the nucleus, which means they're harder to remove, and they're hardest to remove out of all of these, so therefore it has the highest first ionization energy. Now we have to compare silicon and phosphorus, so Si and P. Well, phosphorus actually has a higher Zeph than silicon, which has a lower Zeph, and in addition, phosphorus has a half-filled sublevel for its 3p sublevel, which means that it's going to be even harder to remove the electron from there. So because this has a higher Zeph and it even has a stable, half-filled 3p sublevel, then that means that the electrons that are removed from phosphorus are going to be pretty difficult to remove. So therefore has a higher ionization energy and beats silicon. So phosphorus will be the second highest, and the third highest, or the second lowest, would be silicon, and the answer would be, let's see, which one has that? So it would be A. And if you were unsure about silicon and phosphorus, you would have immediately noticed that if you could determine which one has the highest first ionization energy, then you could have figured out that it was A, because nitrogen has the highest first ionization energy. So the answer would have been A either way. We have 2 questions left, so let's get to it. An orbital has the radio wave function shown below. What orbital is it? Well, if you remember the shapes I told you to memorize, if it suddenly dips down at the beginning, then it's going to be an S sublevel, and all of these have S sublevels as the answer choice, so that doesn't really help us. So what else can help us? Well, we can see how many times it intercepts the x-axis, so it intercepts here and here, and over here it doesn't intercept because it kind of just levels off and it never touches the x-axis because it's asymptotic. So it intercepts 2 times, so there are 2 radio nodes, and remember the equation for radio nodes is n minus l minus 1, and we know what L is because an s orbital has an L of 0. So solving this equation, you immediately figure out that n is equal to 3, and therefore you're looking at a 3s orbital, and C is your answer. So yeah, next question. This question, I admit, is pretty difficult, and just like the previous questions when we started from number 15, this question also comes from the Chemistry Olympiad, so it's pretty hard, but we could do this. So a hydrogen atom emits light as it changes from a state with a principal quantum number n plus 3 to a state with principal quantum number n. Which change causes the greatest change in the energy of the emitted photon? So for this question, I didn't need any numbers because I just drew a diagram. And if you remember at the end of video 4.2, I told you that as you go up in n, the energy gap actually decreases until, it hits 0. And these energy gaps decrease over time, and I'll draw a very careful diagram of this because it's actually necessary for this question. So on the next slide, I'll show you how that works. So I'll draw this as n equals 1, and then n equals 2 will be here, and then I'll draw even a smaller gap, n equals 3, even a smaller gap than that, n equals 4, and then even a smaller gap than that, n equals 5, and even a smaller gap than that, and that'll be n equals 6, and that would be enough for me. And let's take a look at the question and see how this picture might help us solve the question. So it says a quantum number, or a principal quantum number, n plus 3, and remember the principal quantum number is the same thing as the principal energy level. It's, the n. So it says it goes from n plus 3 to n. And, I hate doing variables, but sometimes we just have to do variables, and n is just a variable in this case. And n plus 3 would be the energy state. So let me put n right here, and n plus 3 would be right there. And let's just label the rest: n plus 4, n plus 2, n plus 1, n, and then n minus 1. So notice how instead of using numbers, we are using variables now, and it doesn't matter because if n was equal to 2, then this would be 1, and this would be 3, and this is just like what we did before. So let me just label these. So let's pretend that n is 2, n plus 1 is 3, this is 4, 5, 6, and this would be 1. So see how they relate, and this is just like a simulation. So this will help us solve the question, as I just said before. So it says, which change causes the greatest change in the energy of the emitted photon? So it's saying that at first you have a photon that's released when it goes from n plus 3 to n, and the amount of energy in that photon is equal to, the energy level here minus the energy level here, and that would be the energy of the photon that's released. So this bar in orange will show you the amount of energy in the photon that was released when the electron hops from n equals 3 to n. Now the question is asking which change to one of these states causes the greatest change in the energy of the emitted photon. So I'll show you later how that looks like. A, the initial state is changed to n plus 4. So it's saying instead of n plus 3, it started off as n plus 4. So if an electron started at n plus 4 and it dropped to n, then it would release a photon with an energy that is this much, which is slightly greater than before. So we can label this as A. Now, what's the second answer choice? The initial state is changed to n plus 2. So now we have the initial state at n plus 2 hopping to n, and the energy change associated with that is this much, and that's the amount of energy in the photon that got released. So notice how it's a little bit lower than our original, and this will be labeled as B. So now let's look at C. The final state is changed to n plus 1. So if the final state is changed to n plus 1, then the electron will go from n plus 3 to n plus 1. And the energy change associated with that will be, about this much. So it's in black. And that energy is the amount of energy in the photon. So this would be C. And D says the final state is changed to n minus 1. So it's saying that the initial state stays the same, but the final state is n minus 1. So the initial state is there, and the final state is there. So the amount of energy in the photon that got released is equal to, the energy here minus the energy here, and that would be, the height difference between these two. And this would be the amount of energy in the photon if it went from n plus 3 to n minus 1. So this would be D. Now, the question asks is, what change causes the greatest change in the energy of the emitted photon? So which of these following alterations cause the greatest change in the energy of the emitted photon? So remember, the energy in the photon initially is this, and it's asking which of the following changes cause the greatest change in this value, which is the energy of the emitted photon originally. So which of the following changed the energy the most drastically? So if you look at A, the difference or change in the energy for the photon was just this much. For B, it was even smaller. For C, it was actually slightly greater. But now take a look at D, it's like, boom, that's the change in energy, or the energy difference between the original photon and the photon for answer choice D. So notice how this is the amount of change, and it's the greatest amount of change, since if you compare the bars, this guy is so much bigger than this guy, and a lot has changed basically. So the greatest change is associated when you make the final state n minus 1, so the answer will be D. And this was a pretty rough question, and not all questions in life are nice, and that just applies to almost anything. So I hope you learned a lot in this video. I hope you understood most of the stuff, or maybe even all of it, and I'll see you next time if you watch another video.